Ampere's law relates two important quantities in physics. The first is the magnetic field, and the second is the electric current that produces that magnetic field. The complete form of Ampere's law looks like this. It involves a closed integral. We write a closed integral like that around a contour. This will be explained in a minute. And it involves an integral that is known as a line integral. And on the right hand side of this equation, it involves a constant which we already know. It is the permeability of free space or permeability of vacuum with a value of 4 pi times 10 to the power minus 7 Tesla meter per ampere, and electric current, capital I. For many special cases, as those cases that we shall encounter in this video, the magnetic field vector and the length element vector, are parallel to each other. That means the angle between them is 0 degrees. So the integrand quite simply reduces into B dl. The contour C is a closed loop contour that coincides with the magnetic field itself. One application of this Ampere's law is to calculate the magnetic field produced by a system of electric currents. We shall look at two such systems. The first system is a very long wire that is carrying a current, say I ampere. The second system is a very long solenoid with, say, N turns that is also carrying a current, say I ampere. So let's first look at a long wire carrying a current I ampere. The current extends all the way from minus infinity, let's say, to infinity. We know magnetic fields appear in loops. So using the right-hand rule, the magnetic field would appear in concentric circles like that, enclosing the electric current. And the direction of this magnetic field can be determined in the following manner. By curling your right-hand fingers so as to grab this wire and aligning your right-hand thumb in the direction of the electric current, you see that the direction of the magnetic field follows the direction of your curl of your fingers in the following manner. So you see the direction of the magnetic field that this current produces is also like that. An important point to note is that this is a circle with a certain radius, let's call it R. So at any point on that circle, the magnitude of the magnetic field is the same. So the magnetic field, the magnitude of the magnetic field represented by that circular arrow, is a function of that distance R. We want to know what this expression is. So for the calculation purpose, let's look at one particular magnetic field loop. Let's say with a radius R. Let's write down the complete expression for Ampere's theorem, and that is given by this expression, as we have seen a few minutes ago. Now, how do we define the length element? Now, we mentioned that the magnetic field and the length element are parallel to each other at any point on this contour C. So if I have a general element, let's call it dl, the direction of dl is that way. You see that the direction of dl and the direction of the magnetic field is the same. So the dot product simply becomes b dl, and this is the integral that we need to integrate. Now we also know b is constant everywhere at that particular distance, namely r. So this integral will simply become b integral dl, which is just b, the length of that circle. The length of the circle with the radius r is 2 pi r. Equating b 2 pi r, which is the left-hand side of this Ampere's law, to the right-hand side, which is mu naught times the electric current, I, we can solve the magnitude of the magnetic field at a distance r from where the current is. And that simply becomes mu naught I over 2 pi r. Now this is the expression for the magnetic field of a very long wire carrying a current I. The second system that we want to look at is long solenoid. So this is a system, a very long solenoid carrying certain amount of current. Let's say the current is I. Now this is a very long solenoid, so the solenoid extends from minus infinity to infinity. The right-hand rule suggests the magnetic field created by this current I is along the axis of the solenoid, as represented by these red arrows. Because it's a very long solenoid, there is no magnetic field outside the solenoid. So the magnetic field outside on both sides of the solenoid is 0 Tesla. But we do know that they form closed loops. Magnetic fields form closed loops. In this case, the loop would look something like this. So that is the magnetic field shown above, and it closes at an infinite distance like that. So this is the minus infinity, and this is the plus infinity. And this distance here is very large, presumably infinity as well. And this is the contour C that we will use in our Ampere's law. Of course, in this case, let's assume the solenoid has n turns. Now let's start with the calculation. Ampere's theorem states mu naught I equals the integral C b dl, where the contour C is represented by these dotted lines that coincide with the magnetic field. So they close at infinite distance, like that, at infinity. So that is the contour. So the only place in the contour where the magnetic field is non-zero is at the center of the solenoid. So the right-hand side of this integral will simply becomes b, and the b at the center of the solenoid is constant. It can be taken out. A closed contour of dl. Note that the length element, dl, and the direction of the magnetic field, which is also going leftward, is the same, so this will turn into that. So what is this total length? The total length is the total length of the solenoid, which is very long. Let's for the moment assume it's capital L. So the right-hand side of Ampere's law will simply become B times capital L. Another thing to note is that this solenoid has n turns. So on the left-hand side, you have to include that number of turns there because they contribute to the total current. So equating the left-hand side to the right-hand side, you will get mu naught In equals B times capital L. And we can solve for the magnetic field, the axis of that solenoid, as quite simply mu naught I n over capital L. This quantity in the bracket, the number of turns over the total length of the solenoid, is known as the number of turns per unit length. Thus, we can simply write the expression for the magnetic field of a solenoid in the following form: mu naught times current times number of turns per unit length of the solenoid. Let's look at the following problem. Two long straight parallel wires are separated by a distance 20 cm. So this is wire 1 and this is wire 2. They are very long and the separation distance is 20 centimeters. the wires carry equal currents of 3 ampere. So this is 3 ampere, this is 3 ampere in the same direction, parallel to each other. Now find the magnetic field, or rather the magnitude of the magnetic field at 2 points. The first point is point A. Point A is situated in the middle of the 2 wires. So this distance between this wire and the point A is 10 cm, and the distance between that wire and point A is also 10 cm. So A is situated midway between the 2 wires. And also at point B is 10 cm from the lower wire, but 30 cm from the upper wire. So let's first look at the magnetic field produced by these 2 wires at point A. From the right-hand rule, if you grab the upper wire with your right hand, your thumb is pointing in the direction of the current, and the direction of your curl of your right hand fingers should point in the direction of the magnetic field, which will appear as concentric circles. So at point A, you will see that the direction of the magnetic field, because the curls are like that, it will be pointing into the plane. So this is the magnetic field created by the upper wire. The magnitude of the magnetic field created by the upper wire is quite simply the expression that we have determined before. It's mu naught times the current, which is 3 ampere, over 2 pi, distance is 0.1 meter. 10 cm has been converted into meter. Now the lower wire. Using the same right-hand rule, the concentric circle for the magnetic field created by this lower wire at point A would look something like that. So at point A, the magnetic field created by the lower wire actually will come out of the plane, and its magnitude is also the same as the magnitude that we have computed for the upper wire, namely mu naught, they carry the same current, over 2 pi times the distance, which is 0.1 meter. So if you take the direction that is coming out of the board to be positive and direction going into the board to be negative, for example, you see that when you sum the 2 contributions, they simply cancel, giving you a net magnetic field of 0 Tesla exactly at the midpoint. Now let's look at point B. The same right-hand rules. Let's do the upper wire first. Upper wire. So the magnetic field that this wire produces at point B, that would also appear like that in loops. And one such loop, that distance is given by that sketch. And at that point B, the direction of that magnetic field will go into the board. The magnitude of it is given by mu naught, current is 3, over 2 pi, the distance from the upper wire to the point of observation, which is 0.3 meter. Now the lower wire. The lower wire will also produce loop like that, and at point B, it would have a magnitude of mu naught times 3 over 2 pi. The distance is now 0.1 meter. They both are going into the board, so they have the same sign. Let's call that plus and plus, for example. So the net field at point B, or the total field, is the result of summing this field and that field, and that's going to give you mu naught over pi times 20 Tesla, and it's going into the board. So this expression is what you would get when you sum that and that, namely the sum right here. Thank you for watching.